Hey folks, we saw our first serious reflection, not just one of the simple equality reflections, and I wanted to talk a little bit more about the difference between propositions and functions that we write. So there's a bunch of different angles to go in on this. The angle I'm going to take here is sort of an operational one. That is to say, propositions in computation are really different in how you use them and the sort of affordances they offer you. Um, Propositions often let you say things that would be really hard to say in computation. We're not seeing that here. We'll see it, I think, starting on day 16. We'll start to see really meaningful, interesting propositions. Whereas computation lets you sort of compute rather than have it actually prove. So I'm going to show you this latter aspect where there's a thing that computation lets you do that proofs don't, and sometimes this reflection makes things much easier for you. First, though, I want to highlight a key distinction, which is that propositions don't compute at all. So you can't run them. So here's a definition of uh, a function you might care about. I can't imagine why anyone would. There's only one even prime. But here's a function, is even prime n. And it asks, okay, if n is equal to 2, writing the proposition, then true, otherwise false. Now, this fails and it says, look, you can't write a program on propositions. So you might have done this as a typo early on, maybe out of habit you did a double equal from whatever language you were learning first. Um, you cannot, in a general way, in Coq, ask if a proposition is true or false. Be like, okay, well, if it's true, we'll do this. If it's false, we'll do that. Um, in the video after this, I'm going to talk a little bit more about why you can't do that. But for now, I want to stress that that's not a way that it works. Okay, so this doesn't work. So a nice thing about using booleans is, well, you can compute. So if you just wanted to run the code, you can run it. So let's look at some trivial facts and see how different approaches to proving them maybe let you see the bonuses of computation as opposed to propositions. And later on, we'll see things that propositions can do that computation can do only with great challenge. Okay, so here we want to prove that 1,000 is even. So one way to do that is to say, okay, there exists a k, 1,000 equals double k. So let's do that proof. Um, Now, again, math whizzes might have jumped straight to 500. And that's indeed the proof you want to do here. The most direct proof, right, is you just say there exists a number 500, and then, okay, at that point you compute. Right? You just run it and see that that's the right answer. Now, the Boolean proof is simpler, right? You just say is even b 1000. You say, hey, Cock, can you figure that out for me? And it says, yep, you're right. My programs terminate 1000 even b 1000. That returns true. You're good. Now, the cool thing about reflection is it lets us get the best of both worlds. So here we can prove this theorem, right? Where we get to find out what the K is, right? We're going to build the package, right? Here, we don't get to learn anything about which number it was. So that's like kind of too bad. Here, we're going to write the theorem that lets us know which number it was. There exists some K that we can open up and look at it. But then what we'll do is we're going to use our reflection to change sort of the world that we're in. So even bool prop changes our goal from exist K as an at 1000 equals double K to just even b 1000 equals true. So what? Well, even bool prop, that's the reflection lemma that we proved earlier, right? On one line, there we go. That's maybe a little small, I'm sorry. That's better. Right? Even bool prop says these two utterances are equivalent. If you were going to say this, then you could just as easily say this. So what reflection lets us do is it lets us state things in, I think, the more useful way. Right here, we have an existential where we get to know about K. But then prove things in the much easier way where it's like, okay, just run the function that figures it out for us. Okay. Um, this is all maybe still a little bit abstract. That's fine. In the next video, I'm going to talk about some sort of like trickinesses in Cox logic related to particularly this issue. And then as time goes on, let's just keep an open mind, right? We'll see that there are times when this sort of versatility, whether something's happening in computation or whether something's happening in proof, ends up being really useful for our work in Coq. Okay, that's all I wanted to say here. I'll see you in the next and last video, and then we'll be done with today.